Hi, welcome to the Calculus 1 course, which is mainly about differential calculus. Right, I have some, most information is updated on the blackboard already. If you didn't check the course information, you can go ahead and check it. Right, which most about the distribution and what we will cover for the entire semester. Right, and well, for differential calculus, which the precalculus was somehow introducing some key important components, right? Some important material has covered in our precalculus, which we still need to take a review. Right, for precal, which very important thing, right, the first one is increasing, decreasing, and constant intervals. Right, by definition, that these intervals must be open interval. Which instance using parentheses as open interval doesn't like the closed interval, the endpoints in open interval does not count it. Right, so it could be for increasing that for x1 for x2 is bigger than x1, then the f of x2 is bigger than f of x1, that the function in the graph is climbing up. Right? And for decreasing, similarly, when x1 is less than x2, but the function value or the y value is smaller. And we'll see what is the function later, right? Still take a look of it, the formal definition. And constant means, well, no matter what x1, x2 is changing, right? Which one is which, but the f of x1 and f of x2, their y values are leaving constant, which will be a horizontal line. For instance, right, that could be an equation or at least a function. A function, well, one x value give only one y value. That is a function. Every x have only one y value is defined. Right? Even though here the left piece is the endpoint is -2, 2. It is defined at 2, but here the value -2, 0 is not defined. On the right here is a semicircle, right? On the right, the point is 2, 0 is not defined at that point, but it is approaching to 0 as x goes to 2. And also on this piece, as x goes to 2 from the right, the y value is approaching to 4, but it's not defined, right? It's an open circle. Then the function is going down. So what we can see, and of course the semicircle, the middle point is 0, 2. what we can see is, well, we have some interval is increasing, some interval is decreasing. When we talk about increase, decrease, or constant intervals, are open intervals. Right? So we have increase, the increasing interval, we have the piece that climbing up is the left piece of the semicircle. But that's the only thing we have. Other things from left to right, they are going down, and going down. Increased piece, we only have interval for x value from -2 to the middle of 0. Right. To the 0 of the x value here. Right, that's our increasing interval. And decreasing interval, we have, well, the first piece from all the left going down to the x value of -2. Right, so we have first piece -infinity to -2. The second one from the 0 here, it's going down to x value of +2. And the third piece is from this +2 to +infinity. They break down as 2 since this function is cut into 2 pieces, right? Neither point is defined, neither the 2, 0 or the 2, 4 was defined, but as we're talking about the open interval, we only see the value of it approaches to. Right? On the left, the function value is approaches to 0. On the right, or from the right, the function value is approaches to 4. Right? They have different approach, but it was the function value or the y value is not defined. Doesn't like we have a solid point here, which is defined. This on 2 was not defined, but doesn't matter. Right? Asking for increasing or decreasing intervals, we always use the open intervals, which not count the endpoints in. Only count in is the value approach. Therefore, for 2 different pieces of the function, we'll have 2 different intervals. Cannot be put them together. Right? They cannot be put together. So that was before I erased was the formal definition. Not that formal, but it's the definition. Right? And when you see the curve, you'll see more easier. Right? That decrease is going down, increase is going up. Right? Intuitively, should be making sense. Right? And when we talk about intervals, are the intervals of the x value. From -2 to 0, it is climbing up. From -infinity to -2, from 0 to 2, and from 2 to infinity, from these 3 pieces, the functions are going down, are actually the decreasing interval. So, in our approach to our learning is we'll figure out in what case functions are increasing or decreasing, in which intervals the function are increasing or decreasing, and of course the shape are looking differently, right? Together with their shape, or in other words called concavity, right? Climbing up may be not that fast, or climbing up a little faster, like the graph of log or the graph of exponent, maybe differently. Here is we have a semicircle, right? It's not that fast. Depending on that, which is called concavity. It could be this way or could be this way. They're both increasing but with different concavity. We'll see them later. And together with the interval of increase or decrease, we'll get the interval and we're able to sketch the graph of a function, right, of a given function. Right, so that is the first thing we are talking about, right? To are basically just reminding us what will happen for the increase, decrease, and constant intervals. The second is difference of quotient. Given an arbitrary function f of x and any point x over there, have the y value called f of x. Then we go into a distance called h, and the second point called x plus h. There is a y value corresponding to it called f of x plus h. Then what we have learned from our precalculus was the difference quotient is the difference of our y value minus divided by the difference of our x value, which is x plus h minus x. That is the h here, And graphically, we can form a secant line in between the 2 points, and that actually the difference was the difference of y over the difference of x. The difference of y over the difference of x, which is the tangent value of this angle, which the line formed by the line and the x-axis. This tangent value of the angle is called the slope of this line, pretty much. And when we see the straight line, that's difference of y over difference of x, which is the tangent of the theta. The theta is the angle formed by the line and the x-axis, which the tangent value of the angle is actually called the secant line's slope, the slope of the secant line. Then that is simply the difference of quotient. So to define difference of quotient, that something may be simplified in the case of x plus h, then the difference could be simplified at the end. Maybe something else could be done. We are able to cancelling out the h on the top and on the bottom, then get to the last step before we do something else, before the final step, to get the full or the final expression of the difference of quotient. So let's see. For the function x squared minus 5x plus 4 to find the difference of quotient. A couple steps. The first step is to find f of x plus h. Someone use delta x as the difference of x, but actually while we use h, it's also appropriate. I prefer to use h since well, when we see the delta x and we do some other expression, maybe it will be more confused, right? The delta x actually is a single notation. It's not delta times x. It's just one notation called delta x, which stands for the difference of x. But we could use h instead to be a little less confused, right? Then when we go into the operations, we'll be a little clearer of what we will do, right? Of what we're doing. So the function was defined by the x, such that it's the variable x squared minus 5 times the variable x plus 4. Now instead, the variable now is x plus h. So every time we see the variable x, it will be substituted by x plus h. Right? That's what it's doing. But perfect square, perfect cubic formula, or some other formulas maybe we should know. Right? The perfect square at least should be okay. Right? So we should at least remember that. Right, the sum square of two objects, that will be the sum of squares, and the middle interacting term will be twice. Which means x squared plus h squared, interacting term, that will be 2xh. And then distribute the second one, minus 5x minus 5h plus 4. That is the first step to list out or to write out what is x plus h. If it could be simplified, we'll simplify it. Maybe we cannot simplify, then we can simplify the difference if possible. Or even difference cannot be simplified, we can simplify the quotient. Right? I always have a way to simplify it. For the difference of x plus h and f of x, that is the expression on the numerator, we take x plus h, which is the expression after simplifying, or just expanding out, and nothing simplify it. And the reason why we put in the parenthesis is because we are doing a subtraction. Right? Subtraction, we have to put a parenthesis to make sure that everything after the negative sign will be changing sign. Right? If you know that, of course, you could skip this step, but it is always good to write the essential step. And then we have seen that, well, x squared minus 5x plus 4 is what we have and what we want to take off. Right, but if you can see, you could just simply taking off. If it is a little harder, then we're expanding everything out. Right? X squared 2xh minus x squared plus 5x minus 4. So we figure out from this step that the x squared cancelled out, negative 5x cancel out with positive 5x, and positive 4 cancel with a negative 4. Right? To have all those things cancelled, then we leave 2xh plus h squared minus 5h. Right, that is what we leave out. And it could be more simplified. Or we have figured out that every term contains the h, that we can take the h out, we'll get 2x plus h minus 5. Now, while we're taking out the h, well, we could leave it, but it will be a little more clear that everything has h as the term. Right, so when we factor it out, we are able to cancel the denominator, which is the single h there. Right? The third step is just to divide. We have the first step, right, with is f of x plus h. The second step, we wrote down the quotient and simplified towards the end. The third step, we're able to just cancel the h out. The denominator is cancelled out, which is just 1 here, and when we divide every quotient, every term by 1, that we get just 2x plus h minus 5. Right? That's what we left over. So for the function f of x equals x squared minus 5x plus 4, the difference of quotient when x is the arbitrary variable x, the h is the difference of x values, then it will be the expression of 2x plus h minus 5 as the slope of the secant line. For the square root of x, we're also able to find the difference of quotient. So, doing step by step. Step 1, f of x plus h. Substitute underneath the square root, that's the variable, which for f of x plus h underneath will become x plus h. What we get is square root of x plus h. Which nothing can be simplified, it cannot be separated. We can only simplify the square root when we have a product. And the factor of the product maybe is a perfect square, then we can be taken out from a square root. We cannot do it when it's some difference or so. Product same as quotient, in other words. But when we have sum or quotient, we cannot separate or simplify the radicals. And then the only thing we can do is find the difference. Well, the difference, since only singletons we have, which means we have only single terms, that the difference is very obvious, that one term minus the other term. Still, we have nothing to do with this. But when we can see the difference of quotient here, we may have something figured out so is able to simplify. Right, for any arbitrary x, for any arbitrary h values, as the difference of x, right? It can be, this expression always holds, right? But it is not simplified enough that we have still the h over here, maybe it is not that much good, right? For instance, if our h is 0, then this expression simply cannot find any value because we have square root of x minus square root of x over 0, that we get the 0 over 0 is called indeterminate form, which for any defined function, the indeterminate form is the thing we try to avoid, especially for h is not a variable, for h is arbitrary constant. It should be holds for any h, right? But this expression simply doesn't hold for the expression when h is equal to 0, right? It may be, after simplifying, right, it could be hold for any arbitrary h, but here in this case it cannot be correct for, it cannot be defined actually, right, for this h to be arbitrary value, but it's supposed to be. Right? So the way is we need to figure out a way, right, to make this h on the denominator simply could be cancelled, like what we see before. Right? So what we could do is rationalize. Well, we have two radicals, and multiply its conjugate is the way to rationalize the rational radical expression. Right, multiply the conjugate to causing the difference of quotient, which the difference of quotient is the conjugate pair product multiplied together will be the difference of squares of the bases. Right? So by doing the conjugate pair multiplying, what we get is on the denominator, nothing could be simplified. But on the numerator, we have the difference of squares of the quotient. I mean, not the quotient, difference of squares of the square roots, which we have square root x plus h squared, that is x plus h, minus the square root of x squared, that is simply the x. And x squared and x plus h minus x, we get the expression to be h only. So before we simplify, we have the h playing important terms that, well, this expression should be arbitrarily defining in the domain of the function, should be anything which should be defined. But for the h to be 0, actually affects the expression to be indeterminate form. Right? Then after we do the conjugate pair multiplying, we eliminate the effective of our h. In this expression, 1 over square root of x plus h plus radical x, this term h could be any arbitrary constant that will not affect our quotient here, right? our value here. Which means the secant line could be any possible values for any h to be 0, to be 1, to be 2, any h values, arbitrary values. So that is the how we do the radicals, right? We just multiply the conjugate pair to get the expression. And then, see something else. I believe the rational expression is also the one you have seen in your precalculus. When we do the difference of quotient, we substitute the x with x plus h on the denominator. if you want, you could put parentheses, but that's nothing else but just 1 over x plus h plus 3. Right, to put parentheses when we substitute would be a good habit. Maybe sometimes we have negative sign, sometimes we have other coefficient in front of our x, we don't know, right? Maybe the power we have. So putting parentheses will always be a benefit. Right? So that will be kind of important, right, to do the substitution. Then we take the difference. Right, the f of x plus h was the expression, the f of x was given. Right, the difference of two quotients, we could combine them together. Right, the thing was called finding the least common denominator, or actually least common multiple of the denominator, and to multiply, and we get a single fraction, basically. And here for totally two different, even though they look similar, but they are two different denominators, the least common multiple will be just their products. Right, so for the entire fraction, we'll multiply by x plus h plus 3, x plus 3 as the common denominator. Actually not multiplying them, but this will be our common denominator. And that's what we have for the same denominator of x plus h plus 3 times x plus 3. Our first numerator to be x plus 3, the second to be x plus h plus 3. Then we do the difference. We get x plus 3 minus x minus h minus 3. Which everything x and the negative x, 3 and negative 3 are cancelled. X is always negative x, 3 cancels with negative 3, leave out the only term is negative h. Right, that's the term left over. And when we divide this expression, the third step, we divide the difference by h, which we get the slope, right? That is negative h over x plus h plus 3 divided by h. So it looks like nothing else we could do, but we have the expression is not a simple fraction. We have a compounded fraction, which we have the main fraction is the division of h, but the numerator is also the fraction. That we do a compounded is fraction that a over b divided by c over d. We could change it into multiply. Let's keep the numerator and flip the denominator, and that become product. That is what we can do. Negative h, x plus h plus 3, x plus 3. The h was kind of the expression of h over 1. So when we flip it, it becomes product and 1 over h, which now all h on the numerator and denominator could be crossed out and leave 1 alone. And our new expression becomes negative 1 over x plus h plus 3 times x plus 3. Right, that is the type of the difference of quotient when we do a rational expression, right? To find the difference by combining them together to a single fraction, then dividing by h to see what the term is left over. Okay. The difference of quotient is important. That when the h is large, well, we have from the arbitrary variable x, we are forming a secant line, right? But in the case that h is getting smaller and smaller, like if our h is very short, that the secant line will approach more close to a tangent line, right? And the tangent line is actually another name called rate of change of the point x, right? Then some term important we'll see in our course is when the h is very, very small, what it is. We have a special name, which the slope of secant line will become the slope of tangent line, and that is that name is in our course name, right? The differential calculus. That tangent line slope, the collection of the slope of the tangent line for arbitrary x variables is called derivative, right? Derivative of a function. That is what we'll see in our course. Right, so a couple of expressions we have seen, the three functions, the difference of quotient. After the entire thing we do, if our h is 0, we'll see a variable or we'll see an expression not containing the h. That will be the expression called derivative. And we'll see that in more detail, which is similar as this thing, in more detail later in chapter 3.